Great, thank you very much. OK, I believe this is on. Yeah, thanks again. This has been an incredible day, great conference. Really happy to be here, and I'm very honored to be closing this out today. So we'll just get right to it. Yeah, just a little bit about me to start. My name is Dan Phillips. I work for a little company called Loophole Labs. We do a few different things, but the main thing that we do is this product called architect.run. This is completely unrelated to my talk, but this is what I work on at my day job. It's a way that you can take VMs and migrate them with zero downtime. It's really cool. Check it out. On the internet, I usually use this handle, d_Philla, on Twitter, X, LinkedIn, places like that. Some variation thereof on Blue Sky and those places. OK, just to get right into it. Why do people like containers? This is, we're going to sort of talk at a high level and then move into things more specific as we get into the Boxer project. So there's lots of reasons, but I think one of the most important reasons people like containers is because they see them as a primitive. People who are involved in the cloud-native space, we've kind of come to accept the idea that containers are a cloud-native primitive, right? They're sort of a fundamental unit of compute. And we don't go much lower than that in lots of different services that exist today. They just work when they work. They just work, right? And one of the great things about them just working is that you don't need to know how the runtimes are implemented to have a lot of things work. In fact, I would go as far as to bet that most people who use containers don't know, and maybe don't care exactly how they work. They just work. I think a lot of developers see containers as just a small VM, just like a mini VM, right? Most people, when they first come across them, they think, OK, this is kind of like a VM, and I'll use it like a VM. I'll SSH into it. I'll attach a session, and I can poke around in it. And it's just a little VM, even though it's not. Containers before Docker. So containers before Docker. Containers existed before Docker. Docker was built on LXC. There were lots of ways that you could use things. I think C groups were introduced into the kernel in 2006. There was isolation in the form of a container. You just had to assemble it all yourself, right? There were quite a few things that you had to do to make it work, and most application developers did not know about it. Docker gave us a developer experience. And that developer experience has kind of entered our consciousness as this abstraction, because that's really all it is an abstraction across different runtimes. The runtimes have changed. The particular details have changed about how the runtimes work. But this correct abstraction gave way to a primitive. So at Loophole Labs, we have been doing Wasm in production for the last 2 years with a product called Scale, scale.sh. Scale is a plugin framework that we developed. We started working on it about 3 years ago. And I'm not going to get into the details now. If you want to check it out, scale.sh is the place. Fully open source. You can play with it. We support Rust, Go, TypeScript. And it's an extremely performant plugin framework that we use for our control plane for our other products. We learned a lot about what developers need and what they stumble on and how they use WebAssembly through this process. One of the big things that we learned is that devs, okay, and by devs I mean application developers, not systems engineers specifically, they don't want to rewrite system code for benefits that they see as marginal or that they don't fully understand. We can, by the way, if you haven't noticed, I'm not talking about what WebAssembly is or how it works, because I think everyone here gets it for the most part. So we're just kind of getting into it. But yeah, application developers, you can tell them Wasm is safer, but they may not understand exactly why. You can show them that it's faster, and that's cool, but they're not going to rewrite system-level code to make their Python, Ruby, PHP, Java app work. Most of them won't. Some will. The simpler you can make the DevX, the better. Too many caveats kill adoption, okay? A choice then often comes up, which is, do I run unmodified code, like on a native platform, or do I use this cool new Wasm tool? And that's kind of been like a binary choice for a lot of people. And it's not just our product, it's also many other Wasm products that are out there today. ¿Por qué no los dos, right? What if we could have both? Why not both? What if we could have the compatibility of native code with the benefits of Wasm? This is a representation of me eating my cake and having it too and eating it too, right? So these approaches are in opposition, right? What a container does is that it starts with everything. It starts with the whole world. It starts with a kernel. It starts with an operating system. It starts with the need for C groups, the need for namespaces. It starts with the CNI, the CSI, the CRI, and all these things that need to be there to give you this one little shipping container, right? That only you can see stuff in, which it's much harder to break out of than it used to be, but it's still just a contained thing that's hiding all of this complexity. What if we started with the opposite approach, and we took only what we need, and we added system functionality as needed, but with native compatibility, And this is the opposite approach. So, thinking about WebAssembly and thinking about a new primitive, we have kind of toyed with different ideas for the last few years. We sort of started looking at the current state of the art back in like 2021. Thinking about, this was pre-component model, this is when we were referring to things as nanoprocesses and different ideas around how we can bring Unix processes into Wasm, but not really all the Unix philosophies. And then if you look on the other side, thinking about the primitives that exist in current native systems with Unix, which is the primitive? Is it a process or is it a file descriptor? Because everything is a file, even though it's not, and processes are how things work, even though you need file descriptors to access them, and depending on the context. So there was a lot of confusion there. People have talked about Plan 9. I think there's actually not supposed to be a space, Plan space 9. A lot of really cool ideals, principles, and aspirations come from Plan 9. But specifically, there's some interesting things around per-process namespaces. And there's also the idea that it's distributed first, right? Every process in Plan 9 has its own, the original idea was for it to have its own CPU. It's kind of interesting. So, when we started looking at how we could kind of adopt the good parts of Unix and think about other more aspirational things and how we could get system code to work for arbitrary POSIX code, we of course looked at the Linux kernel. And we started looking through Linux kernel source code and trying to extract the functionality as discrete components. And the results, so if you've ever tried to do this, it's not as easy as it seems. It sounds great in practice, but we just started with the Linux-VFS. We were like, OK, this must be something that we can take and use, but the amount of dependencies and the amount of coupled logic, is a 30-year-old project that the entire world's infrastructure runs on. There's a lot there, right? So even people who in the microkernel and unikernel space typically end up rewriting all these different levels of things without being able to reuse existing parts of the Linux kernel. So, OK, what's the closest? Then the closest thing then is one level up, which is actually where some of these standards come from. libCs, right? libCs give you a standard POSIX interface. And what if we took these standard POSIX interfaces and we fulfill the implementations ourselves, right? That gives us the ability to layer these implementations, right? We'll talk more about this. And that leads me to a project called Marcotte. Marcotte is sort of a sub-project of Boxer, which is basically an amalgamation of muscle libC and glibC with virtualized layers that are generated ad hoc when you use it, right? So Marcotte takes the entire POSIX specification, and the goal is to implement every single POSIX function, right? And we're at about 60%, right? This is just a matrix of what's supported. It's great because in POSIX there are things that don't even touch the kernel. There are things that require the kernel. There are things that you can emulate, and there's everything in between, right? You'll see that things like process and thread management are still missing. Signals are still missing. And we'll talk about that here in a second. OK. So the difference, though, is this is a libC that doesn't wrap implementations. Rather, what it does is create virtualized functionality as much as possible. And when you can't virtualize something, it tries to find the right interface at the right level for stuff that you need, which we'll talk about also. You need a file system, right? You need a file system for every module, maybe a file system for every process, if you have the concept of a process. And we kind of started just with getting just the right amounts of compatibility with POSIX, where we could bring most of the stuff that people need and save the hard stuff, like async I/O and syncing and things like this, right? And that's where we came up with the Wasm-VFS. Wasm-VFS is a project that we've worked on for a couple years now, and it implements most POSIX file system calls with a couple exceptions, right? So what we do then is we have Marcotte, which creates these layers. Marcotte uses the file system for every single module, every single process, and it brings this in together so you can call these standard libC file system functions, but under the hood it uses a Rust-based VFS. And people say, okay, well, it's a VFS, data's not persisted, like how could you use a virtualized file system for everything? And usually my answer is that you already are using a virtualized file system for most things if you're using a Unix system. Every time you access a file system, it is through the abstraction of the Linux VFS, right? It's just that underlying file stores and persistence is something that is abstracted away for most application developers. So we put this all together, maybe all together in one box, if you will. And maybe we have something like a new primitive. But first, one of the things that I'd like to point out is that interfaces matter. One of the great things about Docker that they've created is this beautiful file that we're all familiar with, which is a Docker file. People who don't even know what Docker is, who are developers, can read this file and kind of get a sense of what this thing is, what the fundamental unit of compute will be based on this very simple and declarative structure. So we already have a beautiful DevX that Docker gives us, and it's incredible prior art, so that's what we are going to use as our interface also. And that's where Boxer comes in. Boxer allows you to take a container declaration, and it spits out a Wasm binary, and host plugin functions, right? So you can take a Docker file, and in theory, soon, at some point in my life, when I get more time to work on this, any arbitrary Docker file, and it will create a universally runnable Wasm binary. So what is in a Wasm box, just to recap, based on everything we talked about so far? We have a base layer. The base layer is generated by Marcotte, which is a full libC and as much virtualization as possible, right? In that virtualization, we have a virtualized file system and system code layers, okay? We have a runtime. So this bundles a runtime, but it's specific, and you can swap runtimes. Right now it's Wasm time, but we've also experimented with WAS0 and Whammer. It shouldn't matter, because the difference is that the host functions that you need for anything like networking, or if you want to actually use signals, or if you're on some sort of operating system where you want to wrap specific architecture-specific code, then you can use these host plugins, right? And then, of course, the user source code. Imports and exports. Yeah, so talking about how this works and how these are broken out into subcomponents and submodules is something that I'm not going to get into at this talk, but if you'd like to talk more about it, we can talk after. Yeah. So, quick demo. Yeah, it's kind of big enough. OK, so we have a Docker file here. Not all of the directives are supported yet, but these directives that you see are. OK, so let's see. Great. The necessary ASCII art, of course. What we're going to do is we're going to take this Docker file, all right, and we're going to do box builds Docker file. OK. We'll do a box ls, right? Oh, and one thing I didn't mention is that I've already compiled the C code that I'm going to run. And the very important thing about this C code, all this does is very simple for the purpose of a demo. It prints out 100 numbers, all good. The most important thing is this, right? This would usually indicate that we're running this on a native platform. But because we are using Boxer, specifically with Marcotte, you can include stdio and get everything that comes with. Okay. So you'll also notice that it's kind of big for that code that we just compiled. But you have to remember, and there's been no sort of optimization done with this, this brings in everything that we can virtualize for all of what we've combined from glibc and muscle, right? Not just stdio for now. So we'll do box run. Yay, printed. That's great. And now we'll do something else. Let's do box run web. Oh, of course this wouldn't work. Yay, also worked here too. And now that I have this here in my browser, running the exact same code that we just ran on my local machine, here, what if we had a little script that I could download the entire runtime with the box precompiled and run it safely on my local machine. That's what, in theory, we can do here as soon as I build this functionality in. And then, yeah, further, we could take this exact same box, because it's just a Wasm binary, right? And we could deploy it on the best site deployer that you've never heard of, because this is a personal project of mine that I never talked about. But we could use Boxer, and what we can do here is deploy that same code to a server, and the result being the same. So that's the same code running in 3 different places. And what I personally love about this, and what got me really excited about WebAssembly, is the fact that that exact same code from a container definition can be run in the browser, can be run on the server, can be run locally on your machine, but also it can be run anywhere where there's a Wasm runtime. So we can also run this on an IoT device, on embedded devices. If we work on the size constraints, a lot more places are theoretically possible. If you'd like to sign up for more announcements and releases, check out boxer.dev. We have a little sign-up thing for your email. This is an image that I had ChatGPT make for me. I thought it came out pretty well. Kind of encapsulates the whole idea, right? A box versus a shipping container. Obviously, there's a lot to explain here. This is a high-level overview. But basically, Boxer, to summarize, it virtualizes Unix-like system functionality, okay? Run anything in Wasm like you would on native. That's the goal. Our goal, too, is that this is going to work for about 95% of container workloads. Obviously, if you are using a container and you're doing something with native architecture-specific code, that is not going to work, and it's not going to be something that we really support. We could get around this with emulation if we really wanted to, but that would be multiple cans of worms that are probably well beyond the scope of the project. Right now, it's about 60%. File system operations, networking, and then libC functions like math, localization, things like this that don't touch the kernel. How do we do this? Networking, signals, threads, IPC, process management. Yes, all of these things could be their own talk, and there's a lot to each one of them. So if you're going to be around tonight or tomorrow and you'd like to talk more, I would love to get into all of these. So the goals. One of the loftiest goals is to create a better bootstrap a better compile to Wasm story, right? I don't know if many people in this room run Wasm services, but when people come to Wasm, they want the simplest thing possible. The sort of thesis here, too, is that with Docker containers, the sort of way that containers worked previous to Docker, it was too hard for most people to figure out until it was put into a nice DevX and people didn't have to think about the underlying constraints. The result is that you get something safer, faster, smaller, and more universal. If you noticed in the Docker file that we used for the example, we use from scratch, right? But there's no reason, theoretically, that with this sort of compilation story that we couldn't use something like Alpine Lattice if we were to get all of the user space programs compiled accordingly, right? Right now, it's a work in progress, but we are working towards more feature parity all the time. One of the anti-goals. So this is not a replacement for WASI. That's a very important point. This is at a different level of abstraction. There's no reason that you can't have, at a very, very high level, and this is another sort of debatable thing, but there's no reason that you can't virtualize things to the point where you have POSIX compatibility and capability-based security. There's a lot there. That by itself could be a whole other talk, too. So what does this enable? Truly isomorphic deployable primitives. Run the same code like I just did in your browser, on your local machine, on a server, right? That also changes how we can distribute compute across multiple dimensions. You can take these things in these different places and combine them, right? It wouldn't be a talk in 2025 if we didn't mention AI, of course. So AI code that's being made more and more every day. People have said that there will be a 100x increase in software produced, and it'll be produced by people who know maybe maybe they don't know as much about what they're doing with security, and there's going to be so much more. It would be nice to have a primitive that could work well, that we could trust for all of this untrusted code that's about to be thrust into the world. And we can do that with a familiar DevX, just with something that's smaller, safer, faster, and more universal. Lastly, one interesting point, and this is kind of interesting to me with Wasm in particular, is there's a vast amount of unutilized compute in the world, right? Idle compute. In fact, just in this room, there's a huge amount of idle compute that's just sitting here, right? And in most of your phones and computers, guess what kind of runtime you have on those devices, right? That's an interesting thing. Obviously, if we want to harness that compute, people have tried this type of stuff in the past and failed. But there's a lot of interesting ways that we could talk about verifying execution, moving running workloads, all sorts of cool stuff in a really, really interesting future. So that's it. Thank you. I think I have a couple minutes for questions, if anyone's interested. Don't all jump at once. OK, cool, great.
Hello?
Oh,
Yeah.
Sorry, yeah, go ahead. Oh, hey, how are you?
Yeah. How do you build a C program to WebAssembly? Which toolchain are you using?
Yeah, good, really good question. So using Clang, right? And what we do is instead of just using standard Clang, we do all the linking ourselves against this modified libC that we have in Marcotte, right? So when you run this, instead of just relying on what's on the host like you would in a native platform, we are basically providing the SCIO headers and source code via Marcotte. Yeah. Other questions? Oscar.
Is it me first? Hey, over here.
Oh, sorry.
On that, so like how, for example, if you're using Emscripten, I don't know for sure. I think Emscripten, if you do printf, it goes to your console log.
Yep.
Whereas in yours, it goes to the canvas. Do you
Yeah.
what's the sort of design impetus behind do you think Clang is always going to be the appropriate solution, I guess?
That's a great question. I mean, so each of these things, I didn't talk about any of these terminal devices, but we'd like to keep the design as similar as possible. So we basically have miniature emulated terminal devices that attach to each process in Marcotte that then are plugged into each host, right? And these are the host plugins, right? So it's kind of like when you, the analogy at a high level is if you attach something, like you attach to a Docker session, what you're actually doing there is creating a virtualized T2I environment and then attaching to that process and reading things in bytes at a time. That's basically how we do it here too.
Okay.
Yeah.
So it seems like you're doing all native Wasm. You're not doing any kind of emulation at all?
Native Wasm, what do you mean?
Like, I mean, so like the C program, you said you compiled it with Clang. Did it compile to like x86 or
Oh, no. That compiles to Wasm-32. Yeah. So it compiles to Wasm-32, but to get the standard library stuff, we're providing the standard library.
Got it. And so are there any plans to do any kind of emulation for if I have a Docker file that I just copy in a random binary?
Yeah, that's a great question. That is something that is probably well beyond the scope of this project, right? So if you were to copy in like an x86 binary and then try to like run this, there are some interesting projects out there, like those guys, I think in Japan, who are doing this, where they take the, I think it's like ARM binaries and translate them on the fly. That would be something to look at, but it's not something that we've handled here. Basically, one of the steps that I skipped is there's a sort of like before the box build step, that binary, there's a box compile step, and that's the one extra step that's not sort of in the similar API to the Docker CLI, right? So you box compile that binary, which of course under the hood, this is a WebAssembly function that we're just executing, but it's the same DevX, so you don't have to think about the difference. That is the one difference, though. Yeah.
Very cool.
Thanks.
How is it security-wise? Because you have the code and you build the box, the container.
Mm-hmm.
Then you still have control over where you go from inside the container outside. So how is that isolation level?
Yeah. So the best way to think about this is that like we are taking functionality that was once sort of separated between user space and kernel space, and we're bringing it all into user space. But that user space is within the guest Wasm. Right? So there are many things that I didn't discuss on purpose, things like POSIX spawn, fork exec v, these things. Because the way that that's handled is through, instead of spawning new processes that are new Wasm modules, you can spawn what the user thinks are processes, but within the same module. So basically, the security guarantee is that all you can see here is all you have access to. And because every process has its own file system, that's all it can see, right? And because we didn't talk about how the networking stack works, but because the networking stack is also virtualized and also brought into the same space, the only sort of attack vector with things moving in and out are with things that are that cross to the host, right? So it gives you the illusion that you're in a POSIX environment, but it's actually much more restricted to the specific process that you're running. Yeah. There's about 1 million details in there, though, that we could talk about. Yeah. Oh, Daniel. Yeah. Hey.
Yes, that's a pretty cool presentation. I have one question. What is the most, you say it's about 60% implemented systish. What's the most complex thing that you have managed to compile, and how does it compare in terms of size and performance to say Emscripten, for example?
That's a great question. I'll take those in reverse order. So comparing to Emscripten, I have no idea because I haven't run the benchmarks. But I can tell you because this is like a virtualized first approach instead of, so like right now, it's interesting too because Emscripten is moving towards a virtualized file system approach, right? But they were using a JavaScript-based one, and that was like the calls across the boundary for any sort of significantly high I/O. There would be a cost, right? So the interesting thing about performance on a general, in a general sense that I can say is that the interesting thing by sort of doing this process of bringing all of the system functionality into the Wasm space is that the most performance are literally just imports and exports, right? And most things are not implemented by the host, okay? So the interesting thing there is that with high IOPS and stuff like this, the cost of system calls drops to nothing, right? So like context switching doesn't exist in this format, right? However, there are other concerns, right? So like the difference in when you do need to do things that are below the networking stack. So what we actually do with the networking stack is we go all the way down to where the NIC is, and then we virtualize the stack to there, then we pass things across the host there. So you can use things without an operating system if there's a NIC, which is kind of a cool networking thing to discuss. So yeah, it's a trade-off. It's a trade-off. It would really depend on your workload. The other question, too, the hardest thing to compile, I would say, is there is a lot of history baked into libC, a lot, right? And there are things in there that before I worked on this project, I didn't even, like, the fact that there's localization functions in libC is fascinating to me, right? The math functionality is extensive, right? And some of it is like things that are specific to different architectures, right? And then making things like, just out of the box, the very first challenge was like making the type definitions work for everything, right? So we had to redefine what type definitions were, and that was probably the hardest part, because it was like, okay, well, I mean, do we want to stick with like 32-bit, or what do we have here? This is like, if you look at how libCs are implemented, they have like these top-level header files. They have source definitions, but then they have definitions for every single architecture that they support, right? And those implement really crazy things in different ways, right? And so, yeah, I would say the hardest part was actually wrapping the file system libC calls with this Rust-based virtual file system that we built. That took a long time to sort of get right. And there's still, file systems are incredibly hard, and I don't claim to be an expert, right? And so there's a lot there, and there's probably more bugs that I'm not even aware of. So, anybody else? Cool, thanks again, appreciate it.